Okay, friends, we're looking at problem 4b now. This problem asks us to look through a bunch of statements and determine which ones are true and which ones are false. When they're true, we're asked to prove it. When we're false, we're asked to give a counterexample. Now, for you guys, they give the hint that you can use the counterexample from the 6-element matrix group that we looked at before. That's all well and good. I'm going to encourage you guys to do that. Towards showing you as many different groups as possible, I have a problem in mind that I want to look at, and I'll pick a different group. Just keep showing you guys as much different stuff as possible. So the first one is, let's look at 4, which says if x squared equals x, then x equals e. This is true. All I have to do is remember that since I'm dealing with a group, I can multiply both of these by x inverse. And here, this cancels down to give e. And we remember that x squared means x times x. These cancel down to get e. So x is e. Great. The other one I want to do is false. That one was number 5. It says if x is any group element, there is always another group element with y squared equals x. In other words, there's always a square root of sorts. Right? You can think of y as the square root of x. This one's false. And a relatively simple counterexample is as follows. Consider the group G, which is the set consisting of just 2 elements, 1 and -1, with operation multiplication. Usual multiplication here, right? Well, we know how to multiply normal numbers, so we can ask, is there a literal now square root of -1? Not in G, there isn't. That's a general fact that you might know, but if you don't know, there's only 2 elements to check. The proposition says that there should be some element y in G with this property. So if x is -1, I just check y equals 1 as y squared equal 1. Not the same thing as -1. What about y equals -1? Y squared's 1 there also. Still not -1. So working with very small groups sometimes helps us find counterexamples. That's why Pinter recommends you look at the 6-element group. But even just knowing the integers mod n, right? We have z mod nz. We have this group now, which we could call plus or minus 1 as a group. And then we have the 6-element matrix group. This is already a pretty good collection of unusual, I'll say, groups, right? Not just integers or rational numbers or real numbers, but genuinely different groups, which one can search for counterexamples. So if you like this group, you're welcome to search it. You're also welcome to try these guys too. Sometimes these can be very simple ways to find counterexamples.